In the soft glow of the late 18th century, when the world was still awakening to the mysteries of electricity and magnetism, a quiet yet brilliant mind began to take shape in the small German town of Erlangen. Johann Christoph Schweigger was born on April 8, 1779, into a world of change, a time when empires clashed, revolutions stirred, and science was breaking free from the shadows of superstition. His early years unfolded not in the grand halls of power, but within a modest home filled with curiosity and learning. It was here that the seeds of a lifelong passion for knowledge were sown. From a young age, Schweigger displayed a temperament both curious and introspective. He was fascinated by the world around him, by how natural forces seemed to move with precision and purpose. While many of his peers were drawn to the traditions of religion or politics, young Johann found his calling in observation. He would spend hours watching the flicker of candles, the movement of shadows, and the play of light on water. To him, the world was not chaos, it was an intricate mechanism waiting to be understood. In the 18th century, Germany was a mosaic of small states and principalities, each fostering its own centers of education. The University of Erlangen, near his birthplace, was one such beacon of learning. It was there that Schweigger's intellectual journey began in earnest. Enrolling at the University of Erlangen, he immersed himself in the study of philosophy and the natural sciences, disciplines that, in his time, were still deeply intertwined. His professors quickly recognized his sharp intellect and his disciplined curiosity. He was not merely content with reading the works of others, he questioned, analyzed, and debated them. To Schweigger, knowledge was not a collection of facts. It was a living force that demanded exploration. His early education was shaped by the Enlightenment ideals that swept through Europe, the belief that reason and observation could unlock the secrets of the universe. Thinkers like Immanuel Kant, Voltaire, and Newton had already transformed the intellectual landscape, and Schweigger was determined to follow in their footsteps. He began exploring the boundaries between philosophy and experimental science, fascinated by the idea that human understanding could be expanded through careful experimentation. During his years at Erlangen, Schweigger developed a keen interest in chemistry and physics, fields that were rapidly evolving. Electricity, in particular, had become one of the most mysterious phenomena of the age. Scientists were just beginning to realize that it was not merely a curiosity, but a powerful force of nature. The experiments of Benjamin Franklin and Luigi Galvani had ignited a spark in the scientific community. The concept of animal electricity, the strange current that made frog legs twitch, was still hotly debated. For Schweigger, these mysteries became irresistible. He began conducting his own small experiments, fascinated by how invisible currents could produce visible effects. But Schweigger's early life was not one of ease or privilege. The political turmoil of the Napoleonic era cast a long shadow over Germany. As French armies swept across Europe, universities faced financial hardship, and scholars often worked under great pressure. Yet Schweigger's determination never faltered. He believed that science was a refuge from the chaos of politics, a universal language that connected all nations and all thinkers. This belief would guide him throughout his life, shaping not only his career, but also his outlook on humanity's progress. After completing his studies, Schweigger's academic excellence earned him recognition among Germany's growing community of scientists. He began working as a lecturer, sharing his passion for the natural sciences with young students. His teaching style was unlike others of his time. It was vivid, hands-on, and deeply engaging. Schweigger understood that science was not something to be memorized, it was something to be experienced. He encouraged his students to experiment, to observe, and to challenge established ideas. This innovative approach made him a respected figure among both peers and pupils. By the early 1800s, Schweigger's intellectual curiosity had expanded beyond the classroom. He began collaborating with other scholars and publishing his own research papers, many of which focused on chemical reactions, electrochemistry, and the behavior of materials under electric influence. These works may seem modest today, but in his time they represented the cutting edge of experimental science. Schweigger was part of a generation that was transforming natural philosophy into what we now call modern physics. One of the defining features of Schweigger's academic background was his ability to combine disciplines that others often kept separate. He saw no boundary between chemistry and physics or between philosophy and mathematics. To him, they were all interconnected, different languages describing the same universe. This holistic way of thinking allowed him to approach scientific problems with a unique perspective. It was this mindset that later enabled him to conceive the galvanometer, an instrument that would bring together the forces of electricity and magnetism into a measurable reality. In these formative years, Schweigger's curiosity often led him to challenge authority. The scientific world of his day was still heavily influenced by classical theories that dated back centuries. Many scientists clung to Aristotelian or Cartesian models of nature. But Schweigger was part of a new generation that demanded proof through observation and experiment. He believed that nature spoke in patterns, not dogmas. His experiments were simple but profound. He would test materials, measure reactions, and document even the smallest irregularities. His notebooks, now largely forgotten, were filled with detailed observations and sketches, each reflecting a mind deeply engaged with the physical world. In addition to his research, Schweigger became involved in the emerging networks of European scholars who exchanged letters, findings, and ideas across borders. These scientific correspondences were the lifeblood of early 19th century research. Through them, Schweigger connected with thinkers who were also exploring electricity and magnetism. Names like Ørsted, Volta, and eventually Faraday. Although he was not as widely known as they were, Schweigger's contributions began to earn quiet recognition among his peers. His work was precise, methodical, and guided by a philosophical belief that truth was universal and discoverable through reason. As a teacher and scholar, Schweigger also played a vital role in shaping future scientists. He inspired curiosity and respect for experimentation. In many ways, he saw himself as a bridge between the old world of speculative philosophy and the new world of empirical science. His students admired his patience, his clarity of thought, and his willingness to admit when nature defied expectation. For Schweigger, every failed experiment was not a defeat but a lesson, another clue to the deeper structure of reality. Yet even as his reputation grew, Schweigger remained humble. He was not driven by fame or wealth, but by the quiet satisfaction of discovery. In an age when some scientists sought recognition through grand theories, Schweigger preferred precision. He believed that progress came not from bold proclamations, but from careful, repeated observation. His dedication to accuracy would later define his invention of the galvanometer, a device built not on speculation, but on measurable truth. The early 19th century was a time of great transformation in Europe, both politically and scientifically. The Industrial Revolution had begun to reshape daily life, and the boundaries between science and technology were beginning to blur. Electricity, once a laboratory curiosity, was starting to reveal its potential for practical use. Schweigger, with his deep understanding of both theory and experiment, stood at the crossroads of this transformation. He understood that science was not just about explaining nature. It was about harnessing it for the betterment of humanity. His early experiences at the University of Erlangen, his struggles during the turbulent Napoleonic years, and his relentless pursuit of understanding all shaped him into a scholar of rare balance. One who combined intellect with imagination, discipline with curiosity. Though he did not yet know it, these qualities would soon lead him to make a discovery that would forever change the way humanity measures and understands electricity. By the time he reached his early 40s, Schweigger had become a respected academic, known for his keen insight and unwavering dedication. But beyond his public life, he remained a deeply reflective man, In his journals, he often wrote about the relationship between man and nature, about how the universe seemed to obey laws both mysterious and mathematical. These writings reveal a mind not only concerned with the technical aspects of science, but with its philosophical depth. To Schweigger, every experiment was a dialogue with nature, a conversation between human curiosity and the silent logic of the cosmos. In the quiet halls of the university, surrounded by instruments, coils of wire, and notes filled with numbers and sketches, Johann Schweigger continued to refine his understanding of the natural world. He may not have sought greatness, but greatness found him. Through his relentless curiosity, his devotion to accuracy, and his faith in the power of reason, the journey of the forgotten father of electromagnetism had truly begun, not with lightning or grand discovery, but with the quiet spark of a mind devoted to truth. As the seasons passed in Erlangen, Johann Schweigger's life began to settle into a rhythm that blended teaching, research, and reflection. The quiet city, with its old stone buildings and tree-lined streets, became the perfect backdrop for a man devoted to thinking. He would rise early, often before sunrise, and spend hours sketching ideas in the margins of his notebooks. These were not random doodles, they were designs, experiments imagined, instruments refined, connections drawn between forces invisible to the naked eye. Every page of his work revealed an imagination shaped by logic, and a logic softened by imagination. The university environment during the first decades of the 19th century was a mixture of intellectual brilliance and constraint. Funding was scarce, instruments were crude, and the boundaries of science were undefined. Yet Schweigger thrived in this environment because it rewarded patience and invention. His lectures became small gatherings of discovery. Students remembered the way his eyes lit up when he spoke of electricity, as though he were describing a living creature rather than a natural phenomenon. He spoke not from authority but from wonder, explaining that the duty of a scientist was to listen to nature until she speaks. Through correspondence, Schweigger began to extend his intellectual reach beyond Erlangen. Letters traveled slowly across Europe, but they carried the lifeblood of scientific exchange. In these pages, Schweigger shared his experimental results and read the thoughts of contemporaries who were also wrestling with the mysteries of electricity. The works of Alessandro Volta, Luigi Galvani, and the newly celebrated Hans Christian Aristide arrived at his desk like revelations. When Aristide demonstrated in 1820 that an electric current could deflect a magnetic needle, Schweigger immediately recognized the deeper meaning of the experiment. To most observers, it was simply a curiosity. To Schweigger, it was evidence of an underlying unity between two forces long thought separate. He began to reproduce and refine Aristide's experiment. His laboratory, little more than a converted room filled with copper wire, magnets, and glass jars, became a theater of discovery. The air smelled of ozone and heated metal, the scent of early electricity. Schweigger wound wires in tight coils, connecting them to primitive voltaic cells, watching the tiny compass needle twitch and sway. These movements were faint, but to him they were language, a whisper from nature telling him that the electric current was shaping the magnetic field around it. The more turns he added to the coil, the stronger the effect became. In that moment of realization, Schweigger understood that the number of loops multiplied the force, amplifying the magnetic deflection. What he was seeing was not merely a reaction, it was a measurable relationship. That insight would become the foundation for his greatest creation, the galvanometer. In building it, Schweigger combined the precision of a philosopher with the ingenuity of an engineer. He crafted a coil of wire through which electric current would pass and placed a magnetic needle at its center. The current produced a magnetic field that caused the needle to move, indicating both the presence and relative strength of the current. For the first time, humanity could see electricity at work. It was no longer invisible lightning, it became a measurable, quantifiable force. While the galvanometer would later earn Schweigger his place in scientific history, the years leading to it were filled with patient labor and quiet determination. He often worked alone, with little financial support, crafting his own materials by hand. Each improvement, tighter coils, purer metals, more stable connections, brought clearer results. The invention reflected not only his skill, but also the depth of his education. His grounding in chemistry helped him understand the materials, his studies in mathematics guided his measurements, his philosophical training gave him the patience to search for meaning beyond the data. The broader scientific community began to take notice. Letters praising his experiments appeared in German journals, and soon the Schweigger multiplier, as it was first called, became known across Europe. It provided the essential tool for every laboratory studying electromagnetism. Scientists such as André-Marie Ampère and Michael Faraday would later depend on this device to explore their own discoveries. In many ways, Schweigger had given them sight, the ability to measure what could previously only be guessed. Yet even as his reputation grew, Schweigger himself remained modest. He published his findings without grand self-promotion, content that his work would speak for itself. This humility, however, may have contributed to his historical obscurity. Others built upon his foundation and became famous for the structures they raised, while the man who had laid the cornerstone faded quietly into the background. He seemed unconcerned by this. To him, the goal was understanding, not recognition. His life outside the laboratory was equally disciplined. Schweigger maintained a simple lifestyle, devoted to teaching and writing. He often spoke of the moral dimension of science, insisting that knowledge carried responsibility. He warned that the same electricity which could light cities might also be turned to destruction if guided by greed or ignorance. This moral clarity came from the same philosophical roots that had shaped his youth, the belief that reason must serve humanity, not dominate it. As decades passed, Schweigger's curiosity never dimmed. He continued to explore the natural sciences broadly, studying optics, thermodynamics, and even early concepts of electrochemistry. He founded and edited scientific journals to share new discoveries, nurturing a community of thinkers who would carry his work forward. These journals became platforms for young scientists to publish their ideas, expanding the culture of open exchange that defined early modern physics. Though he rarely traveled, Schweigger's ideas journeyed far. His galvanometer was refined by others and incorporated into ever more precise instruments. With it, scientists measured tiny currents, mapped magnetic fields, and eventually developed the technologies that powered telegraphy and, later, electrical engineering. The wire coils that now fill motors, transformers, and sensors can trace their lineage back to the humble loops Schweigger wound with his own hands. In his later years, the world around him began to transform. Steam engines roared through the countryside, factories rose, and cities glowed with the first flickers of electric light. Schweigger watched these changes with both pride and caution. He saw in them the realization of the scientific dream, the practical use of natural forces for progress, but also the danger of losing sight of science's deeper purpose. For him, knowledge without wisdom was like current without a compass, powerful, but directionless. Despite his contributions, official recognition remained limited. Honors were few, and as newer generations of scientists rose to fame, his name appeared less often in textbooks and journals. Yet among the careful historians of physics, Schweigger's influence never vanished completely. They saw in him the essential qualities of the true scientist: patience, precision, and humility. He was not the kind of man to chase glory, he was the kind who quietly made glory possible for others. When Johann Schweigger passed away in 1857, the world was already racing toward an electrical age that his work had helped ignite. The telegraph lines stretching across continents, the experiments leading toward the dynamo and the motor, all bore traces of his insight. Though his funeral was modest, his legacy was vast. The coils of his galvanometer were, in a sense, the first heartbeat of the electrical world. In the decades that followed, as Faraday's and Maxwell's theories flourished and practical electricity became the lifeblood of modern civilization, Schweigger's name slowly receded into footnotes. But his story did not disappear completely. For those who look back carefully, he remained a symbol of the forgotten pioneer, the scholar who did the quiet work that made revolutions possible. His life reminds us that science is not only built by the giants who stand in the light, but also by those who labor faithfully in the shadows. Even now, his journey offers timeless lessons. It teaches that genuine discovery often begins in curiosity unclouded by ambition. It shows that education, when guided by imagination and discipline, can transform a student into a pioneer. And it proves that even in an age of limited resources, a determined mind can create instruments that change how humanity perceives the world. When one reflects on Schweigger's early life and academic background, it becomes clear that his achievements were not accidents of genius, but the natural outcome of character. His education at Erlangen instilled in him a respect for both reasoning and evidence. His experiences during Europe's political upheaval taught him perseverance. His years as a teacher developed in him a gift for clarity, for making the unseen visible. And all these threads wove together into the mind that would one day reveal the connection between electricity and magnetism. In a poetic sense, Schweigger's story mirrors the very phenomena he studied. Like electric current, his influence flowed unseen through the wires of scientific progress, bending needles and guiding explorers long after he was gone. His life was a circuit completed, not by fame or fortune, but by fulfillment. The spark that began in his childhood curiosity passed through the coil of his education, amplified through his discoveries, and continues, even now, to generate understanding in every instrument that measures the invisible forces of our world. The camera of history, when it pans across the great landscape of physics, too often focuses on the brightest stars: Faraday, Ampere, Maxwell, Einstein. But if it were to linger for just a moment on the quieter corners, it would find Schweigger, standing by his modest desk in Erlangen, turning a simple coil of wire in his hands, unaware that he has just illuminated a path that others will follow for centuries. His story, told not in headlines but in laboratory notes and patient experiments, remains one of the most authentic expressions of the scientific spirit, curiosity, humility, and the relentless pursuit of truth. Thus, Johann Schweigger's early life and academic background were not merely the opening chapters of a career. They were the foundation of an entire discipline. From the curiosity of a child watching candlelight to the precision of a professor shaping magnetic fields, his journey embodies the transformation of wonder into knowledge. He stands as a reminder that the true father of a revolution is often the one who gives others the tools to see. And so, in the quiet hum of every laboratory, in every measurement of electric current, and in every flicker of magnetic motion, a fragment of Schweigger's spirit endures, a silent, steady presence reminding the world that even the most forgotten figures can shape the very forces that power our universe. The dawn of the 19th century brought with it a strange and growing fascination across Europe. Electricity, once considered a mere curiosity, sparks drawn from amber or glass, was beginning to reveal itself as a powerful and universal force. Yet its nature was still wrapped in mystery. Could this invisible energy, capable of producing shocks and sparks, somehow be connected to the force that guided compass needles and shaped the poles of the earth? To most people, such a thought seemed absurd, but to Johann Schweigger, the idea that electricity and magnetism might be related was not absurd at all, it was irresistible. For Schweigger, curiosity was never idle. It was a living instinct, a quiet but persistent voice urging him to look deeper into the unseen. His early years in physics and chemistry had taught him to recognize patterns where others saw chaos. He understood that the universe often concealed its greatest truths behind simple observations. Electricity and magnetism were both invisible forces, both capable of action at a distance, and both governed by mathematical regularities. These similarities stirred in him a sense that they might share a deeper connection, a hidden law waiting to be uncovered. In the early 1820s, when Schweigger was already a respected academic, a new wave of experiments began to electrify the scientific world. Luigi Galvani's studies on animal electricity and Alessandro Volta's invention of the voltaic pile had turned electricity into a controllable phenomenon. Now scientists could produce steady currents and test their effects on different materials. It was a time of boundless excitement, and it was during this period that Hans Christian Rosted made a discovery that would ignite Schweigger's imagination forever. In 1820, Rosted demonstrated that when an electric current flowed through a wire, it caused a nearby compass needle to move. The magnetic needle, drawn normally to Earth's poles, now deflected as though caught in a new, invisible whirlpool of force. It was one of the most profound revelations in the history of physics, a direct link between electricity and magnetism. When Schweigger read of Rosted's experiment, it was as if the final piece of a long puzzle had fallen into place. His scientific instincts immediately came alive. In the quiet of his study at the University of Halle, Schweigger began to reproduce the experiment with his own materials, simple wires, batteries, and compass needles. The results were small, almost delicate, a faint movement of the needle when current passed through the wire. But to Schweigger, that faint movement was the voice of a universe speaking a new language. He realized that this was not just an isolated effect, it was a gateway into a new realm of science. Electricity could influence magnetism, and if one could understand that relationship deeply enough, it might explain the very structure of the natural world. His curiosity became obsession. Schweigger began experimenting day and night, often by candlelight, sketching diagrams of electric circuits, winding wires in tighter loops, and measuring angles of needle deflection. He noticed that the more loops of wire he made, the stronger the magnetic effect became. It was a moment of insight that would change everything. He understood that by multiplying the loops, by coiling the wire into many turns, he could amplify the magnetic response of the current. This realization was not just practical, it was profound. It meant that the forces of electricity and magnetism were not only connected, but could reinforce each other. This simple but revolutionary idea would lead directly to his invention of the galvanometer. But beyond the invention itself, it revealed the depth of his understanding. Schweigger was not merely building instruments, he was exploring the language of nature. Each coil of wire, each deflection of a needle, told him something about the invisible dance between electric flow and magnetic pull. His notebooks from this period show meticulous records, numbers, sketches, and observations of how changing the current or the number of coils altered the magnetic motion. He was, in effect, mapping the first outlines of what would later become electromagnetic theory. To grasp the magnitude of Schweigger's interest in this relationship, one must imagine the intellectual world he lived in. There were no unified theories, no clear equations describing electromagnetism. The word electromagnetism itself was barely known. Scientists of the time thought of electricity and magnetism as separate, unrelated domains. The compass belonged to sailors and navigators, the battery belonged to chemists. Schweigger's curiosity bridged that divide. He saw what others missed, that both phenomena might be different manifestations of the same natural principle. As he worked, Schweigger drew inspiration from both experiment and philosophy. The Enlightenment had taught him that all of nature was interconnected, that forces once thought distinct might, under the surface, be governed by a single harmony. This belief gave his work a sense of destiny. He once wrote in his notes that to understand nature is to see the same spirit in her many forms. To him, electricity and magnetism were not rivals but siblings, expressions of the same underlying energy. In the candlelit laboratories of early 19th century Europe, Schweigger's work symbolized a new kind of science, one that sought unity instead of separation. He began to correspond with colleagues in Germany and Denmark, sharing his ideas about the connection between these forces. His thoughts were clear. Electricity was not a static or isolated effect. It could move, generate fields, and interact with the physical world in dynamic ways. In these early discussions, Schweigger was already touching upon ideas that would later evolve into the field equations of Maxwell and the modern concept of electromagnetic fields. But Schweigger's fascination was not purely theoretical. He wanted proof, visible, measurable, repeatable. He knew that only through precise measurement could he transform curiosity into certainty. That determination drove him to refine Aristid's experiment until it became a tool for quantification. He wrapped more coils, adjusted current strengths, and aligned needles with mathematical precision. The joy he felt when the needle moved in direct proportion to the current's intensity must have been overwhelming. He had turned an invisible mystery into a predictable pattern, a bridge from speculation to science. Behind every great discovery lies not just brilliance but persistence, and Schweigger's persistence was unmatched. He repeated his experiments dozens of times, testing variables, controlling temperature, adjusting wire thickness, and documenting every result. His laboratory became a landscape of wires, magnets, and batteries, an orchestra of silent forces waiting for their conductor. He knew he was on the verge of something that could transform not only physics, but humanity's understanding of nature itself. The turning point came when he decided to name and formalize his instrument. Using the term galvanometer, derived from Luigi Galvani's earlier work on electricity, Schweigger introduced the world to a device that could reveal the strength of electric currents through magnetic motion. Though it might appear today as a simple coil and needle, in its time it was revolutionary. For the first time, scientists had an eye into the invisible, the ability to see the relationship between electricity and magnetism in motion, to measure it, and to understand it. Schweigger's growing interest in this relationship began to shape not only his experiments, but also his philosophy of science. He started to see all natural forces as parts of a single tapestry woven by universal laws. To him, electricity and magnetism were not random phenomena. They were expressions of an underlying order that connected every particle of the universe. In this sense, his work foreshadowed the great unifications of later centuries, from Maxwell's electromagnetism to Einstein's field theories. At times, Schweigger's obsession isolated him. His colleagues admired his intellect, but could not always understand the depth of his conviction. Many of them were still bound to the older mechanical view of nature, one that treated forces as separate entities acting through direct contact. Schweigger, however, was beginning to think in terms of fields, regions of influence that extended invisibly through space. He could not yet express this idea mathematically, but he could sense it through his instruments. Each movement of the needle was a whisper from this unseen field. In his lectures, he began to describe the connection between electricity and magnetism as a kind of conversation between forces. He told his students that when a current flows, it does not move silently through the wire. It speaks to the space around it, creating patterns that magnetism can hear. Such poetic descriptions made him not just a scientist, but a philosopher of nature. He wanted his students to feel the wonder of discovery, to realize that every experiment was not just an act of measurement, but an act of listening. The early 1820s were also a period of collaboration and rivalry in the scientific world. Scholars across Europe were racing to explore the newly revealed link between electricity and magnetism. Schweigger's galvanometer quickly became a crucial instrument in this race, enabling others to measure currents and refine their theories. It was used by André-Marie Ampère to establish the laws of electromagnetic force, and later by Faraday to explore electromagnetic induction. Thus, even as Schweigger worked quietly in his German study, his instrument became the heartbeat of a revolution spreading across the continent. In these years, Schweigger's fascination deepened into something almost spiritual. He believed that understanding the link between electricity and magnetism was a step toward understanding the unity of nature itself. This belief gave him strength through long nights of experiment and calculation. He wrote that, "On every spark of electricity lies the shadow of the universe's order." These were not the words of a mere technician, they were the reflections of a man who saw science as a path toward truth. By 1823, Schweigger's experiments had made him a respected voice in the growing field of electromagnetism. His publications detailed the relationship between current intensity, wire turns, and magnetic deflection, establishing patterns that would later become the basis for quantitative electromagnetism. His work proved that the strength of a magnetic field depended on both the current and the geometry of the coil, an insight that would echo through every electrical invention to come. And yet, as always, Schweigger's name remained modestly attached to his achievements. The galvanometer was sometimes credited to others. His ideas were expanded and popularized by men with greater influence. But Schweigger never seemed to care for fame. He continued to teach, to write, and to experiment, driven by the same question that had haunted him from the beginning. What is the true relationship between electricity and magnetism? Johann Schweigger's fascination with the relationship between electricity and magnetism did not remain a mere curiosity. It evolved into a lifelong pursuit that would connect his intellect with the pulse of a transforming world. The early 19th century was a time when the invisible forces of nature, electricity, magnetism, and light, were beginning to be questioned, observed, and tamed. Schweigger found himself standing in the middle of this scientific storm, captivated by the possibility that these forces might not be separate at all, but deeply intertwined. His mind became a bridge between chemistry, physics, and natural philosophy, as he sought to decode the mysterious union of two forces that shaped both nature and industry. During his early experiments, Schweigger realized that understanding electricity was not just about sparks or shocks. It was about unseen motion, the kind that could pass through wires and metals and still remain invisible to the human eye. Magnetism, on the other hand, was something tangible yet elusive. One could feel its pull, see its effects, but never observe its essence. He was driven by a question that would guide his work for years. Could these two forces be expressions of the same natural law? It was a question that would not only define his scientific identity, but also place him in a unique position in the history of physics. Schweigger's environment played a major role in shaping his ideas. As a professor at the University of Halle, he was surrounded by a generation of scientists who were daring to imagine new principles of nature. The recent discoveries of Alessandro Volta had electrified Europe, quite literally, and experiments with galvanic cells were becoming common among the scientific elite. Schweigger was fascinated by Volta's pile, the first true battery, because it represented a controlled and continuous source of electrical current. Yet, unlike many of his peers, Schweigger was not satisfied with simply observing electrical flow. He wanted to measure its effects, to see how it interacted with magnetic materials, and to explore whether these invisible forces could be united under a single scientific explanation. His correspondence with other scientists deepened this curiosity. Schweigger followed closely the work of Hans Christian Ehrasted, whose 1820 discovery showed that an electric current could deflect a magnetic needle. This revelation shook the foundations of classical physics, which had long treated electricity and magnetism as unrelated phenomena. Schweigger immediately recognized the importance of Ehrasted's discovery. Where others saw a curious observation, he saw a doorway into a new kind of science, a science of electromagnetic unity. In his laboratory, Schweigger began a series of experiments that would later shape his destiny. He used simple tools: copper wires, iron needles, and magnetic compasses. Yet within these humble instruments, he saw patterns that others overlooked. When an electric current flowed through a coiled wire, he noticed that the magnetic needle inside it moved more strongly than expected. This meant that by increasing the number of wire loops, one could amplify the magnetic effect, a principle that would later become fundamental in electromagnetism. But Schweigger didn't stop there. He realized that this behavior could be turned into something practical, something that could help measure the strength of an electrical current itself. It was in this realization that the seed for his most famous invention, the galvanometer, began to grow. The journey from curiosity to invention was not easy. Schweigger worked in a time before precision instruments and digital aids. His laboratory was modest and resources were limited. Yet his persistence, patience, and creative mind compensated for the lack of equipment. He often relied on his own craftsmanship to create apparatuses that could conduct sensitive measurements. His experiments were marked by repetition, failure, and careful observation. Each trial brought him closer to understanding how magnetism and electricity were linked not by coincidence, but by a fundamental law of nature. The scientific community at that time was divided. Some still doubted that electricity and magnetism could be connected, while others believed Rasted's findings were a rare curiosity. Schweigger's experiments began to offer tangible evidence that this relationship could be measured and manipulated. He theorized that if the flow of electric current could move a magnetic needle, then magnetism itself must be an effect of moving electricity. This realization placed him on the threshold of a new field, electromagnetism, years before the term even gained popularity. Schweigger's work also demonstrated a unique quality. He combined imagination with mathematical logic. He didn't rely solely on empirical observations, he sought patterns and consistencies. He imagined electricity as a kind of fluid, a stream of energy that could generate magnetic fields around it. By adjusting the number of wire turns, he could increase or decrease the strength of this field. This approach reflected his deep understanding of proportionality and his desire to bring numerical precision to an otherwise invisible phenomenon. Beyond the laboratory, Schweigger's intellectual environment fueled his ambition. The age of romantic science, as historians later called it, encouraged thinkers to blend philosophy with natural study. Schweigger believed that nature operated according to hidden harmonies, and it was the duty of the scientist to uncover them. He viewed electricity and magnetism as two expressions of one divine principle, a reflection of balance and unity within nature itself. This philosophical outlook gave his scientific inquiry a sense of purpose and wonder that many modern researchers might find poetic. As Schweigger's experiments advanced, so did his reputation. He began to publish his findings in academic journals, attracting attention across Europe. Though he was never as famous as his contemporaries, his peers respected his rigor and vision. He became a mentor to younger scientists and an advocate for interdisciplinary research, often urging his students to think beyond the boundaries of chemistry or physics alone. For Schweigger, understanding nature meant seeing the connections that linked all forms of matter and energy. His quest for knowledge was not purely theoretical. It carried the weight of application. Schweigger envisioned that if the connection between electricity and magnetism could be understood and controlled, it could lead to new technologies capable of transforming communication, engineering, and even medicine. Though he lived before the age of electric motors and telegraphs, his insight foreshadowed the world we know today. But Schweigger's fascination was not without struggle. The scientific world moved quickly, and as he continued his studies, others such as Ampere, Faraday, and Gauss began making their own discoveries in the same field. Schweigger was aware that he was part of a greater movement in science, yet he remained humble, focusing on precision rather than fame. His goal was not to outshine his peers, but to perfect the understanding of this new relationship between electricity and magnetism. In his writings, Schweigger described the electric current as messenger of motion and force. He saw magnetism as its language, a visible signal of the invisible flow of energy. To him, every deflection of a needle, every flicker of movement, was nature speaking in a code that scientists were just beginning to interpret. This poetic vision of science reflected his belief that discovery was not merely about data. It was about deciphering the living patterns of the universe. Schweigger's determination during this phase of his life laid the groundwork for what would soon become one of the most revolutionary scientific instruments of the century. His pursuit of the link between electricity and magnetism was no longer just an intellectual curiosity. It was an obsession driven by the desire to measure the unmeasurable. Though history would later celebrate others for defining electromagnetism, it was Schweigger who first translated the invisible into the visible, the theoretical into the practical. By the late 1820s, Schweigger's experiments had matured into a system of precision that few others could achieve at the time. His deep interest in the behavior of magnetic fields around electrical conductors gave him the confidence to propose that magnetic forces could be mathematically related to electric current, a notion that would later be validated by Ray and Faraday. This transition from speculative thought to quantifiable observation was the hallmark of Schweigger's scientific genius. He didn't just witness a phenomenon, he gave it meaning and a framework to be studied by generations to come. As the 1830s approached, Schweigger continued refining his theories, sharing them through lectures and writings that inspired a new generation of physicists. His name might not have echoed as loudly as others, but his ideas resonated deeply within the halls of academia. He had proven that curiosity, when coupled with perseverance, could unveil the deepest mysteries of nature. Johann Schweigger's exploration of electricity and magnetism was not just a chapter in science. It was the ignition point of a revolution that would electrify the modern world. Johann Schweigger's journey toward his greatest scientific contribution, the invention of the galvanometer, stands as one of the most fascinating chapters in the history of science. It was a story not born from luxury or grand laboratories, but from a man's persistence, patience, and the fire of curiosity burning inside him. To understand the making of this invention, one must step into Schweigger's world at the dawn of the 19th century, when electricity was still a mystery, magnetism an enigma, and their connection a subject of wonder and debate among Europe's brightest minds. The year was 1820, and the scientific community was in shock. Hans Christian I. Rasted had just demonstrated something astonishing. When an electric current passed through a wire, it could move a nearby magnetic needle. This simple experiment was a revelation. It suggested a link between electricity and magnetism, two forces that scientists had long considered separate. Schweigger, who had been deeply studying both subjects, was captivated. He instantly grasped the significance of Rasted's discovery. Where others saw a strange coincidence, Schweigger saw a hidden principle of nature, something that could be measured, quantified, and transformed into a practical instrument of science. At that time, scientists had no reliable way to measure electric current. Electricity could be produced and observed, but it could not be precisely detected or compared in strength. Schweigger knew that to truly understand this invisible force, it needed to be made visible in some measurable form. He began experimenting with Rasted's principle, using compasses, wires, and simple batteries to explore the interaction between electric current and magnetic needles. Schweigger's laboratory was modest but alive with energy. On his workbench lay tangled copper wires, iron needles, small magnets, and glass jars filled with chemical solutions, each a tool in his search for the unknown. His approach was careful and methodical. He placed a magnetic needle near a conducting wire and observed the deflection caused by an electric current. But soon he realized something extraordinary. When he coiled the wire several times around the needle, the deflection grew stronger. Each turn of the wire seemed to amplify the magnetic effect of the current. This discovery was the key insight. Schweigger understood that by coiling the wire multiple times, he was effectively increasing the strength of the magnetic field generated by the current. The more loops, the greater the effect. This meant that even a small electric current, otherwise too weak to detect, could produce a measurable magnetic response if the wire was wound sufficiently. In that moment, Schweigger had stumbled upon a principle that would forever change the study of electricity. The principle of magnetic amplification through coiled conductors. Driven by excitement, Schweigger refined his setup. He wound a long wire around a magnetic needle mounted on a pivot, allowing it to move freely. When an electric current passed through the coil, the needle responded by deflecting proportionally to the current's strength. He now had a device that could visually indicate the presence and magnitude of electric current. This was the birth of the galvanometer, one of the first instruments to measure electricity in a quantitative way. The first galvanometer was a simple but elegant creation. It consisted of a coil of insulated wire wrapped around a magnetic needle suspended on a pivot inside a wooden or brass frame. The device was delicate and required careful calibration, but it worked. The needle's deflection showed whether a current was present, and the degree of movement provided a measure of its strength. For the first time in history, scientists could see electricity move, not as a spark or flash, but as a controlled, measurable phenomenon. Schweigger's galvanometer was revolutionary. It transformed electricity from a mysterious curiosity into a measurable science. Before its invention, researchers could only infer the presence of electric currents through secondary effects: heat, light, or chemical reactions. Now, with the galvanometer, they could directly observe and record electrical activity with precision. This instrument became the scientist's eye into the invisible world of electrical forces. The implications of this invention were immense. Schweigger's galvanometer became an essential tool for physicists and chemists across Europe. It allowed for the accurate measurement of current in voltaic piles, the study of electromagnetic forces, and the development of quantitative electrochemistry. In the hands of other great scientists, such as André-Marie Ampère, who was formulating the laws of electrodynamics, the galvanometer became indispensable. It provided the experimental proof that electricity could generate magnetism, thus confirming the birth of electromagnetism as a unified field of study. Schweigger's invention was not merely an instrument. It was a turning point in scientific methodology. It marked the transition from qualitative to quantitative science. Before the galvanometer, many discoveries relied on observation and speculation. After it, science began to rely more on measurement, data, and reproducibility. The galvanometer's ability to transform invisible electrical energy into visible motion was symbolic of a new era, the era of precision physics. But Schweigger's achievement was not the result of chance. It was the fruit of perseverance and intellectual vision. He had the rare ability to combine theoretical understanding with experimental craftsmanship. His mind could imagine physical laws, while his hands could build the tools to test them. The galvanometer was born not only from knowledge but also from creativity, the kind of creativity that allows a scientist to see patterns where others see chaos. The simplicity of Schweigger's instrument concealed the depth of its genius. The principle behind it, using coiled wire to magnify the magnetic effect of a current, would later become fundamental to electromagnetism. It was the same principle that would eventually make possible electric motors, telegraphs, and generators. Schweigger's coiled wire around a magnetized needle was the ancestor of every modern electromagnetic device. As word of Schweigger's invention spread, it drew admiration from across the scientific community. His colleagues recognized the instrument's potential and began using it in their own research. Scientists such as Ampère, Ohm, and Faraday relied on galvanometers to measure and verify their theories. Schweigger's name began appearing in publications and academic correspondence, his invention becoming a vital component of nearly every major experiment in electrical science. Yet Schweigger himself remained modest. He continued refining his instrument, improving its sensitivity and accuracy. He designed variations that could detect extremely weak currents, allowing for even finer measurements. He also shared his findings openly, encouraging others to build upon his work. This generosity of spirit reflected his belief that science was a collective pursuit, where each discovery paved the way for greater understanding. Despite his humility, Schweigger must have known that he had achieved something remarkable. He had given scientists a language to communicate with the invisible. The galvanometer became not just an instrument of detection, but a symbol of connection between human curiosity and the hidden rhythms of nature. With every deflection of its needle, it whispered a message from the unseen forces that govern the universe. The invention also had philosophical significance. In an age where natural philosophy and science often intertwined, Schweigger's galvanometer represented a triumph of reason over mystery. It showed that even the most elusive forces could be brought within the reach of human comprehension. His work reflected the Enlightenment spirit, the belief that nature could be understood, measured, and harnessed through intellect and observation. But Schweigger's triumph did not bring him widespread fame. His invention quickly became so fundamental that it began to overshadow its creator. As newer versions of the galvanometer appeared, improved, modified, and adapted, Schweigger's name slowly faded from prominence. Yet every scientist who used the instrument was, knowingly or not, building upon his foundation. Johann Schweigger's galvanometer marked the beginning of a new era in experimental physics. It was the first instrument that truly measured the flow of electric current, the first tool that allowed scientists to translate the invisible into the measurable. From this humble beginning, the science of electromagnetism was born. Even today, the principle behind Schweigger's invention remains unchanged. Modern ammeters, voltmeters, and other electrical measuring devices owe their design to the same concept he discovered 2 centuries ago: the relationship between electric current and magnetic deflection. Schweigger's galvanometer was more than an invention, it was a revelation that reshaped human understanding of the natural world. In every lab where an electric current is measured, in every generator that powers a city, and in every magnetic field that drives technology, the spirit of Johann Schweigger's genius endures. His galvanometer was the bridge between the unknown and the known, between mystery and measurement, a timeless testament to the human drive to make the invisible visible. Johann Schweigger's invention of the galvanometer marked the turning point, not only in his personal scientific journey, but in the entire course of experimental physics. Yet, as with every profound discovery, his path from the first model to scientific recognition was filled with both triumph and quiet struggle. The galvanometer, though simple in appearance, embodied centuries of human curiosity about electricity and magnetism, a curiosity that Schweigger refined into a delicate instrument of precision. In the years following its invention, Schweigger's laboratory became a place of pilgrimage for scholars and students eager to witness the miracle of measuring the invisible. When Schweigger first presented his galvanometer to fellow academics, many could hardly believe what they saw. The idea that an invisible current of electricity could deflect a magnetic needle seemed like something out of a dream. In demonstration after demonstration, Schweigger would connect his coiled apparatus to a voltaic pile, sending a faint current through the loops of wire. Then, before an audience of astonished scientists, the needle would twitch and shift, subtle but undeniable evidence of the link between electricity and magnetism. It was as though Schweigger had found a way to give motion to the unseen forces of nature. In an age before advanced instruments, this was a revelation. Electricity had long been observed through sparks, shocks, and the strange behaviors it caused in metals and chemicals. But now, Schweigger had created a bridge between theory and observation, an apparatus that could measure an electric current in real time. With this invention, the abstract became tangible, and what had been a philosophical curiosity transformed into a measurable science. For the first time, researchers could quantify electric phenomena and compare results with precision. This ability changed the landscape of physics forever. The galvanometer quickly became the central instrument in laboratories across Europe. Scientists who were exploring the boundaries of electromagnetism found that Schweigger's device offered them the key to new discoveries. André-Marie Ampère reused it to develop the laws of electrodynamics, while Georg Ohm used similar instruments to establish his famous relationship between voltage, current, and resistance, what we now call Ohm's law. Each of these achievements rested on Schweigger's foundation, for without the galvanometer's ability to measure current, These laws could not have been proven experimentally. Schweigger's invention was, in many ways, the first step toward the technological age. The principle of the coiled wire amplifying magnetic effects would later form the basis of electromagnetic induction, which Michael Faraday would discover a decade later. The same principle eventually evolved into electric motors, telegraphs, and generators, the very machines that power the modern world. In this sense, Schweigger's galvanometer was not just a tool for measuring electricity, it was the seed from which the entire electrical revolution grew. The instrument also played a crucial role in chemistry and medicine. Galvanic experiments involving chemical decomposition relied on accurate current measurement, and Schweigger's invention made this possible. In medical research, early electrophysiologists used galvanometers to detect nerve impulses and muscular activity, laying the groundwork for modern biophysics. Schweigger could not have imagined the vast reach of his creation, but the principles he discovered extended far beyond physics into almost every field of natural science. Despite the galvanometer's growing influence, Schweigger's personal recognition remained limited. He was not a man who sought fame. His modesty and dedication to teaching kept him from aggressively promoting his work. Many of his contemporaries, more skilled in self-promotion, became better known for discoveries built upon his foundation. Over time, as newer versions of the galvanometer were refined and improved by others, Schweigger's name faded from the public memory. His invention, however, never did. It continued to serve as the silent cornerstone of every electrical experiment. Schweigger's students often spoke of his quiet demeanor and his passion for detail. In his classroom, he encouraged curiosity and experimentation. He would tell his students that science was not about grand theories, but about careful observation and the courage to ask questions no one had dared to ask before. This teaching philosophy shaped a generation of young physicists who went on to expand the field of electromagnetism further. His belief that knowledge should serve humanity echoed through every experiment he conducted. There is a poetic irony in Schweigger's legacy. His instrument, designed to make the invisible visible, ultimately rendered its creator invisible to history. As the 19th century progressed, the galvanometer became so essential to research that it was often treated as an anonymous tool, its origins rarely mentioned. Textbooks referred to it as a standard measuring device, and newer scientists used it without knowing the name of the man who had given it life. Schweigger had unintentionally created a device that transcended its inventor, a tool so perfect that it disappeared into the very fabric of scientific progress. Yet for those who study the roots of electromagnetism, Schweigger's contribution remains undeniable. His galvanometer was the first instrument to provide a quantifiable connection between electric current and magnetic deflection. It was proof that nature's forces could be expressed not in vague observation, but in measurable quantities. This shift, from speculative to measurable science, was one of the great intellectual transformations of the modern age, and Schweigger was one of its unsung pioneers. The later decades of Schweigger's life were filled with quiet satisfaction and continued research. He refined his galvanometer design several times, experimenting with new materials and configurations to improve sensitivity. He also published his observations, hoping to inspire further work. He knew that the age of electromagnetism had only just begun, and that his humble coil and needle were the keys to unlocking a vast and mysterious world of forces. Schweigger's invention soon inspired other designs. Nobili, Poggendorff, and Thomson each developed improved versions of the galvanometer, capable of detecting even smaller currents and providing more accurate readings. These refinements eventually led to the mirror galvanometer, used in telegraphy and early communications technology. Every click of a telegraph key, and every coded message sent across continents in the 19th century, carried within it the echo of Schweigger's discovery. His principle of wire coils amplifying current became the heart of an empire of electricity that would illuminate cities and connect nations. The galvanometer also became a symbol of the new age of precision science. In Schweiger's time, the scientific community was shifting away from philosophical speculation toward empirical methods based on observation, measurement, and experimentation. His instrument embodied that shift. It was not an abstract concept but a tangible, testable, repeatable device. It turned the study of electricity from something mystical into something mechanical, something that could be dissected and understood by logic and mathematics. Schweiger's legacy, though quiet, influenced generations of scientists who may never have known his name. When Maxwell formulated his equations that unified electricity and magnetism, when Faraday visualized lines of force, and when engineers later built the first electric motors, all of them stood, knowingly or not, upon Schweiger's shoulders. His galvanometer was the first real conversation between man and electricity, the first moment when the invisible voice of the current could be heard through the language of movement. In his final years, Schweigger remained a teacher and thinker, devoted to his university and to his students. He never sought wealth or recognition, finding his reward instead in the pursuit of knowledge and the satisfaction of discovery. Those who knew him described him as gentle, introspective, and endlessly curious. To Schweigger, science was not about glory. It was about understanding the harmony of nature. He believed that every discovery, no matter how small, revealed another layer of the divine order hidden within the universe. When he passed away in 1857, the world of science was already racing forward with new inventions and discoveries. Telegraph lines stretched across continents, electric motors began to hum in workshops, and electromagnetic theory was rapidly evolving. Though Schweiger's name was seldom mentioned, every instrument that measured a current, every experiment that relied on deflection, carried a trace of his genius. His galvanometer had become the quiet heartbeat of modern technology. In retrospect, Johann Schweiger's contribution stands as one of the most profound yet overlooked moments in the story of human progress. He gave scientists the ability to measure what could not be seen, to make the intangible tangible. His galvanometer was not just a device, it was a doorway through which humanity stepped into the electrical age. From that moment onward, the invisible forces that shape our universe became subjects of study, understanding, and mastery. The true measure of Schweiger's brilliance lies not in fame but in legacy. His invention still echoes through the wires that carry power across cities, in the sensors that monitor currents in laboratories, and in the instruments that explore the depths of space. The principle he discovered remains unchanged, timeless, and universal. Johann Schweigger, the quiet scholar of Halle, transformed the invisible into the measurable, and in doing so, gave humanity the means to harness the very forces of nature. His galvanometer was more than a tool, it was a symbol of the human spirit's unyielding desire to understand, to see beyond the visible, and to give shape to the mysteries of the universe. Schweiger's invention stands as a testament to a truth as old as science itself, that even in silence, even in obscurity, the light of discovery endures. Johann Schweiger's galvanometer was not just an invention, it was the spark that ignited a revolution in the study of electromagnetism. Before his discovery, electricity and magnetism were seen as separate mysteries, forces that behaved independently with no clear relationship. But Schweiger's instrument changed that forever. For the first time, scientists could see how an electric current could produce magnetic movement, a realization that transformed abstract theory into measurable science. The galvanometer became the bridge that allowed humankind to observe what had once been invisible, turning curiosity into certainty. The device gave researchers a new power, the ability to measure the strength of electric currents with precision. When Schweiger's coiled wire amplified the magnetic effect of a current, it did more than move a needle. It opened a doorway into the hidden structure of nature. Scientists across Europe began using his galvanometer to test new ideas about how electricity flowed, how magnets behaved, and how these forces interacted. It was no longer enough to know that electricity and magnetism existed. Now, their relationship could be studied, compared, and quantified. This single instrument laid the foundation for all future work in electromagnetism. André Marie Ampère used a version of Schweiger's galvanometer to explore the forces between electric currents, leading him to formulate the laws of electrodynamics. Georg Simon Ohm, too, relied on such instruments to measure current and voltage, establishing the principles that govern electric circuits today. Michael Faraday, inspired by these developments, went on to discover electromagnetic induction, the process that makes modern generators and transformers possible. All of these breakthroughs were built upon the measurement principles first made possible by Schweiger's invention. The galvanometer also transformed the laboratory itself. It brought a new era of precision and discipline to experimental science. Instead of relying on sparks or shocks to prove electrical activity, scientists could now record exact deflections, plot data, and compare results. This changed the very culture of research, from speculative curiosity to systematic investigation. In a sense, Schweiger's device was as much a philosophical milestone as a scientific one, symbolizing humanity's growing ability to tame and understand the unseen forces of nature. Its impact stretched beyond physics into chemistry, medicine, and engineering. Chemists used the galvanometer to study electrolysis and the behavior of ions in solution, laying the foundation for electrochemistry. Physicians began experimenting with electrical signals in the human body, leading to early studies in bioelectricity and muscle response. Engineers used the principles behind Schweiger's instrument to design early telegraphs, making long-distance communication through electrical currents a reality. Every wire that carried a signal, every circuit that powered a machine, echoed the same principle that Schweiger had revealed: the link between electric flow and magnetic motion. But perhaps the most profound impact of the galvanometer was its role in unifying natural forces. By showing that electricity could create magnetism, Schweiger's work hinted at a deeper truth, that the universe might operate through interconnected laws rather than separate phenomena. This idea inspired later scientists like James Clerk Maxwell, whose equations would formally unite electricity, magnetism, and light into one grand theory. Maxwell's work, which laid the foundation for modern physics, and even paved the way for Einstein's relativity, can be traced back to the experimental tools and measurements made possible by Schweiger's early invention. In this way, the galvanometer was not merely an instrument, it was a turning point in human understanding. It symbolized the transition from mystery to mastery, from wonder to knowledge. Schweiger's coiled wire and moving needle told a story written in deflection and motion, a story of the invisible made visible. It allowed scientists to read the language of electromagnetism and to build upon it until it became the technological heartbeat of modern civilization. Though time has often forgotten his name, the influence of Johann Schweigger endures in every electromagnetic device we use today, from the smallest sensor to the largest generator. His galvanometer was the silent messenger that carried science into the age of electricity, forever changing the way humanity measures, understands, and harnesses the forces of nature. Johann Schweiger's influence did not end with the galvanometer, it extended into the very heart of scientific collaboration and discovery that followed. His work came at a time when communication between scientists was limited, and experimentation was still guided more by instinct than by precise measurement. Yet Schweigger, through his innovation, gave the scientific community a new common language, a way to translate invisible electrical forces into measurable, shareable results. This simple act of turning movement into data transformed the study of electricity from a scattered pursuit into a structured science. Every deflection on his galvanometer's needle became a statement of truth, a universal symbol understood by researchers from Germany to France, from Britain to Italy. It unified minds across borders, setting the stage for the great discoveries that would define the 19th century. Schweiger's role as a teacher and communicator was also crucial. Beyond his experiments, He was a professor who inspired students to approach natural philosophy with curiosity and rigor. His classrooms were laboratories of imagination, where theories were not merely read but tested, discussed, and challenged. Many of his students carried his methods forward, spreading his influence across Europe. He emphasized that science was not about isolated invention, but about building upon the insights of others, about cooperation between minds and generations. This vision of interconnected progress mirrored the very principles of electromagnetism, forces that act together, unseen yet inseparable. Schweigger himself became a human embodiment of that idea, a connector of thoughts, a transmitter of knowledge. His impact on later scientists was profound. When André-Marie Ampère re-explored the mathematical relationship between currents, he built directly upon Schweigger's instrument. When Georg Simon Ohm developed his law of resistance, it was the galvanometer that allowed him to quantify his results. When Michael Faraday demonstrated electromagnetic induction, he used principles that had first been visualized through Schweigger's coiled wire. Even James Clerk Maxwell's unified theory of electromagnetism, the crown jewel of 19th-century physics, was conceptually rooted in Schweigger's demonstration that electricity and magnetism were not strangers, but partners. Schweigger may not have written the final equations, but his tool gave birth to the evidence that made those equations possible. Outside the laboratory, the ripples of Schweigger's invention began to shape the industrial world. Engineers and inventors saw in his galvanometer not just a scientific curiosity, but a practical device. It became the model for sensitive measuring instruments in telegraphy and electrical communication, helping lay the foundation for a global network of information exchange. The precise control and detection of electric currents made possible by his principles opened the door to technologies that defined the modern age. Telegraphs, electric motors, generators, and later even radio signals. In this sense, Schweigger's influence extends invisibly into every corner of modern life, from the power grids that light our cities to the circuits that drive our machines. Yet despite all of this, history has often overlooked him. While names like Faraday, Ampère, and Maxwell echo through textbooks and laboratories, Schweigger remains a shadowed figure, his contributions hidden behind the brilliance of those who came after. But in truth, every measurement they made, every discovery they confirmed, stood upon the quiet foundation he built. He was the craftsman who gave science a way to see its own progress, to translate the unseen into the observable. Without that bridge, electromagnetism might have remained a collection of isolated experiments, lacking the coherence that turned it into one of the most powerful theories in physics. In reflecting upon Johann Schweigger's legacy, we see a story of humility and transformation. He was not the loudest voice in science, but he was one of its most crucial architects. His galvanometer symbolized a deeper idea, that true progress is not only about invention, but about illumination. It is about revealing what already exists, waiting to be understood. Schweigger's work marked the beginning of that revelation, the moment when electricity and magnetism first spoke to each other through the movement of a needle. From that quiet motion came the thunder of modern technology, the hum of electric power, the pulse of communication that defines our era. His name may fade, but his influence hums eternally in the wires that connect our world, a silent tribute to the forgotten father of electromagnetism. As the scientific world moved rapidly into the 19th century, Johann Schweigger's discoveries quietly wove themselves into the fabric of progress. His galvanometer was more than a laboratory instrument. It was the key that unlocked an entirely new era of measurement and understanding. But its true legacy lay in how it changed the way humanity perceived nature itself. Before Schweigger, scientists observed electricity as a curious, often dangerous force that produced shocks, sparks, and strange chemical reactions. After his invention, electricity became a measurable phenomenon, something that could be studied, predicted, and controlled. It was as though Schweigger had handed humanity a compass for the invisible world, pointing toward the laws that govern the flow of energy in all living and non-living things. The impact of this transformation extended far beyond physics. Schweigger's principles became essential in every field touched by electricity and magnetism. Chemists used galvanometers to study the movement of ions and the reactions that would later define electrochemistry. Doctors began exploring how the human body produced and responded to electrical signals, leading to early developments in electrophysiology and medical devices. Engineers realized that if a needle could move in response to current, then current could, in turn, move machines. From that realization came the birth of electromechanical engineering, the first step toward the motors and generators that power our world. All of these disciplines evolved because Schweigger had provided a way to see what could not be seen, to measure what had once seemed immeasurable. Yet, while Schweigger's work became the backbone of countless scientific advances, the man himself remained a quiet figure in the background. Unlike some of his contemporaries, he did not seek fame or glory. His satisfaction came from discovery, from the elegance of nature's design revealed through experimentation. But as new names rose to prominence, Ampere, Faraday, Maxwell, Schweigger's own began to fade from public memory. His invention became so deeply integrated into scientific practice that people began to forget its origin. Every laboratory had a galvanometer, every scientist relied on its readings, but few remembered the mind that had conceived it. In many ways, Schweigger's success became the reason for his obscurity. His contribution was so fundamental that it vanished into the structure of science itself, like the foundation of a building hidden beneath its magnificent architecture. Still, his legacy endured in subtler ways. The spirit of precision that Schweigger brought to experimentation reshaped the philosophy of science. No longer could theories survive on speculation or anecdotal proof. They had to be tested, quantified, and replicated. The galvanometer symbolized that shift from guesswork to data, from intuition to evidence. It reminded every researcher that progress depends not only on ideas, but on the tools that bring those ideas into measurable reality. Schweigger had taught the scientific world to listen more carefully, to the faint magnetic whispers of an electric current, to the small signs that reveal great truths. Even as technology advanced, Schweigger's influence evolved with it. The basic concept behind his galvanometer, using magnetic deflection to measure current, became the principle behind countless modern instruments. From analog ammeters to complex sensors used in spacecraft, the essence of Schweigger's design still guides engineers and scientists today. Each of these tools, no matter how advanced, carries a trace of his original insight, that motion can reveal force, that observation can unlock understanding. In a very real sense, the machines that monitor our planet's magnetic fields, the devices that scan our hearts, and even the instruments that explore the cosmos all trace their lineage back to Schweigger's first coil of wire. As the world entered the age of electricity, Schweigger's silent influence illuminated every step. The telegraph lines that spanned continents, the dynamos that lit up cities, the motors that drove industry, all owed a debt to the principles he helped uncover. Even the birth of modern electronics, with its intricate circuits and magnetic components, rests upon the same foundation. The invisible forces that Schweigger once revealed with a simple moving needle now power the modern world in ways he could never have imagined. Today, as we look back through the long corridor of scientific history, Johann Schweigger's story reminds us that some of the most transformative figures are not those who shout their names from the rooftops, but those who build the very ground others walk upon. He gave science a new sense of direction, a way to measure and master the unseen. Every flicker of light, every hum of power, every signal that crosses the globe carries the echo of his discovery. Though time may have obscured his name, the rhythm of his work continues, steady, precise, and essential, as if the great galvanometer of history still records his influence in every pulse of electricity that drives the modern age. In the twilight of Johann Schweigger's legacy, The story of his life and work becomes a reflection on how innovation can transcend the limits of its own age. Schweiger's galvanometer had already transformed science, but its true significance lay in how it inspired generations to pursue the unity of natural forces. His invention symbolized the moment when humanity first glimpsed the deep connection between electricity and magnetism. Two powers that once seemed separate, now bound by a single principle. This revelation changed everything. It planted the seed for one of the greatest intellectual revolutions in human history, the understanding that all physical forces might be expressions of one universal law. Schweigger may not have lived to see the full flowering of that idea, but his work was the spark that lit its path. In the decades after his discovery, scientists built upon the foundation he had created. James Clerk Maxwell's equations in the mid-19th century finally united electricity and magnetism into a single framework, electromagnetism. This achievement gave birth to modern physics, transforming not only scientific thought but also the course of civilization itself. Without the galvanometer, without the first precise measurements of current and magnetic deflection, Maxwell's insights might have remained theoretical dreams. Schweiger's contribution was the bridge between intuition and proof, between the invisible world of forces and the tangible realm of observation. Through that bridge walked every great physicist who followed him: Faraday, Hertz, Thomson, and even Einstein, whose theory of relativity was built upon Maxwell's unified field of light and energy. In every sense, Schweiger's work echoed through time, shaping the destiny of science long after his name was forgotten. The story of Johann Schweigger also reveals a timeless truth about human achievement, that progress is a chain of connected minds. No single discovery stands alone. Each idea is born from the insight of those who came before and becomes the foundation for those who will follow. Schweigger understood this better than most. His experiments were never acts of ego, but acts of curiosity. He believed that science was not a race for fame, but a dialogue with nature, a conversation that spanned centuries. That humility became his greatest strength. It allowed him to see clearly, to focus not on personal glory, but on the quiet pursuit of understanding. In doing so, he left behind a legacy far greater than recognition. He left behind the very method by which truth could be discovered. Today, as modern scientists explore quantum fields, electromagnetic waves, and the forces that bind the universe together, they are still guided by the same principle Schweigger revealed: that energy and matter are inseparably linked. From the glowing screens of our devices to the satellites that orbit the Earth, electromagnetism remains the pulse of our civilization. Every spark of power that lights our homes, every transmission that carries our voices across oceans, every digital signal that connects humanity in an instant, all are children of Schweiger's insight. His galvanometer, simple and elegant, was the ancestor of every instrument that measures, monitors, or manipulates electricity today. The quiet motion of its needle foretold the rhythm of the electric age. Yet Schweiger's story also carries a message about the fragility of memory. History often remembers the loudest voices, not the truest pioneers. His name slipped through the cracks of fame, overshadowed by the towering figures who came after him. But to those who look deeper, who trace the lineage of discovery to its roots, Johann Schweigger stands as a figure of immense importance. A man who turned curiosity into a force that reshaped the world. His work reminds us that the progress of humanity depends not only on genius but on persistence, precision, and the courage to explore what lies unseen. As we stand in the modern world surrounded by technology that hums with electromagnetic life, Schweiger's legacy lives all around us. Every current that flows, every magnet that spins, every field that bends space and time owes a silent debt to his vision. He taught the world that nature's secrets reveal themselves not to those who shout, but to those who listen closely, to the subtle motion of a needle, to the faint whisper of a current, to the language of the unseen. Johann Schweigger was not just a physicist, he was a listener of the universe. In the end, his story is one of transformation, of how a single mind, driven by curiosity, helped humanity cross from mystery into mastery. The forgotten father of electromagnetism may rest in the shadows of history, but his discovery burns brightly in every spark that powers the modern world. His name may not echo in the headlines of science, yet his spirit hums through every wire, every circuit, and every field of energy that defines our age. Schweiger's life reminds us that true greatness does not always demand recognition. Sometimes it is enough to leave behind a force that never stops moving, a pulse of discovery that beats through time itself.